Usually, when we talk about a massive global infrastructure crisis, there is this underlying expectation of visibility.
Right, like you can literally see it.
Exactly. Think about, a crumbling suspension bridge. You
Yeah.
drive over it, you look out the window, and you actually see the rusted steel supports.
Yeah, you see the cracked concrete.
Right. Everyone in the car points at it and says, there it is. There's the problem. We need to fix that before it falls into the river.
It's highly motivating when a problem is physical. I mean, we respond to tangible decay. We can photograph the rust, put it on the evening news, and, mobilize a construction crew the very next morning.
But then you step into the world of global finance or telecommunications, government data, and suddenly that crumbling bridge is completely invisible.
Totally invisible.
We are looking at a structural foundation today that is terrifyingly fragile, but you can't see the cracks because the entire structure is made of code.
Decades-old code.
Yeah. And today, we are going to explore a wild, high-stakes rescue mission playing out in real time. We're doing a deep dive into a stack of sources. We've got cutting-edge 2024 through 2026 academic research, empirical benchmark studies like the ATLAS evaluation.
That's a huge one.
Yeah, and major enterprise deployment white papers from cloud giants like AWS and IBM. The core mission here is to understand how specialized multi-agent AI frameworks are attempting to translate millions of lines of half-century-old legacy code into modern Python.
And, it's important to clarify, this isn't an academic exercise. They are doing this to effectively save global financial and governmental infrastructure from what analysts mathematically project as a total operational collapse.
Which is just wild to think about. That is the paradox at the center of this whole thing. And honestly, it directly impacts you listening right now. The most critical systems in your life run on ancient code.
Yeah.
And the only people who actually know how to fix it are retiring en masse.
Yeah.
So let's establish the stakes. What exactly is this code? And, what is it actually running?
Well, we are talking about the bedrock of global commerce. We are talking about the ledgers at your bank, the billing systems for cellular networks.
Federal tax processing?
Exactly. The back end of airline reservations. I mean, these systems process trillions of dollars every single day, and they are doing it almost entirely on COBOL, the common business-oriented language.
Right.
This is code written 40, 50, sometimes 60 years ago, and it is still running on massive mainframe environments, primarily IBM ZOS architectures.
So the sources refer to the human element of this crisis as the silver tsunami, which, sounds catchy, but it feels like there is more to it than just people are getting older.
Yeah, the term is actually a bit reductive, I think, because it implies a standard generational handover. Usually when a senior generation retires, they pass the baton to the junior generation.
To train their replacements.
Right, but what we are experiencing right now is a total, irreversible evaporation of undocumented, deeply embedded institutional knowledge. The youngest active COBOL veterans in the field today are in their late 50s. And the pipeline behind them is completely dry. Universities completely stopped teaching COBOL and codicil programming in their core computer science curricula decades ago.
They pivoted, right.
Yeah, they pivoted to object-oriented languages like Java, then to web frameworks, and now obviously to Python and AI.
So a brilliant 24-year-old computer science grad from MIT can't just step into a bank and take over the mainframe.
Not at all.
It's a complete knowledge vacuum. And reading through these white papers, I realized it's not even just about learning the syntax of COBOL. It's like learning the vocabulary of a new language isn't enough if you don't understand the culture of the country you're visiting.
That is a phenomenal way to frame it. The language itself is almost the easiest part to learn. It's the esoteric ecosystem surrounding the language that creates the real barrier.
The environment.
Exactly. To maintain these mainframes, knowing COBOL is maybe 20% of the job. You have to understand CICS, which are these ancient, incredibly rigid transaction monitors. You have to understand DB2 relational databases mapped out in the 1980s. You have to understand JCL.
Ah, JCL. I kept seeing JCL in the research. What actually is that?
So JCL is Job Control Language. Think of it as the ultimate arcane orchestration format. Before we had modern task schedulers or cloud triggers, mainframes ran on batch jobs.
Okay.
JCL is the script that says, take this massive file of 1 million credit card swipes, wait until 2:00 a.m., feed it into this specific COBOL program, allocate exactly this many bytes of memory on a physical magnetic tape.
Wow, very specific.
And if it fails, trigger this other error handling program. The modern junior developer who's accustomed to cloud-native serverless functions has absolutely zero context for that kind of hardware-coupled orchestration.
Which makes this incredibly relevant to you, the listener.
Rare.
When you swipe your debit card at a coffee shop, or when your cell phone seamlessly hops from one tower to another.
Or when your tax return is processed.
Right. You're relying on an ecosystem that is rapidly becoming an opaque, unmaintainable liability.
And it has forced enterprises into a desperate, highly reactive posture. We're observing major financial institutions rehiring their own retirees as independent consultants.
Right, at massive premiums.
Oh, massive. They are paying 5, sometimes 10 times their original salaries just to bring them back for a few weeks to patch critical vulnerabilities.
But just to keep the lights on.
Exactly. And they have to do this because literally no one else on the payroll knows how a specific CICS transaction routes data into an IMS database.
Okay, let's unpack this.
Yeah.
Because if manual human-driven refactoring is basically dead simply because the humans with the map are leaving the building, the industry has to pivot.
They have no choice.
Right, and the pivot naturally is AI. The goal outlined in all these papers is automated AI transpilation. They want to ingest this monolithic procedural COBOL and spit out modern Python.
Because Python unlocks the modern ecosystem.
Right, they chose Python specifically because it unlocks this massive ecosystem for machine learning, data pipelines, pandas, PyTorch. It brings the bank into the 21st century. But the bigger question the sources raise, and this is where the engineering gets intense, is how do we actually control the AI doing this translation?
You've hit on the foundational debate in AI modernization right now. It is both a philosophical divide and an engineering schism.
The autonomous versus deterministic debate.
Yes. Do we let an AI act as an autonomous agent, meaning we give it the code base, a suite of tools, and say, figure out the best way to translate this, run your own reasoning loops until you succeed? Or do we force the AI into a strictly deterministic, hard-coded pipeline where it has zero freedom to choose its path?
Freedom versus control. And the ATLA's benchmark study in our stack tackles this head on.
It does.
ATLA stands for Autonomous Transpilation for Legacy Application Systems. What blew my mind about this study was how they actually set up the experiment to answer that exact debate.
Yeah, the rigorous methodology of the ATLAS study is what makes it a landmark paper. In software engineering research, it is notoriously difficult to isolate a single variable when dealing with large language models.
Because they're unpredictable.
Exactly. They're inherently non-deterministic. But ATLS managed to isolate the orchestration method as the sole variable. They locked in the underlying language model. They kept the prompts identical, the tools identical, and the source COBOL programs identical.
So literally the only difference was the management style.
Right. Letting the LLM control the flow versus enforcing a rigid deterministic path.
And the results for the autonomous LLM-controlled agents were, well, let's just say catastrophic.
They really exposed a fatal vulnerability in fully agentic workflows when you apply them to highly structured, mission-critical engineering tasks. The core failure point is a phenomenon called agentic drift.
Agentic drift. I want to make sure I'm visualizing this correctly. Is it like a chef who keeps tasting a soup, adding a little salt, then a little water, then some more potatoes, until the pot just overflows and they've completely forgotten the original recipe?
That captures the dynamic perfectly. Imagine you hand an autonomous LLM 1,000 lines of deeply convoluted COBOL. It starts translating, making decent progress, but then it hits a weird, undocumented syntax error. Because it has agency, it tries to self-correct, it pauses the translation and invents a new reasoning loop. It decides to call a tool to analyze the error, then it hallucinates a potential solution, tests it, realizes the solution is wrong.
Calls another tool.
Yes, it calls a different tool to search for context, and suddenly it has fallen into an infinite variable-length reasoning loop. It is completely lost in the woods, burning computational power without advancing the primary goal.
It's overthinking. It's staring at the code, spiraling, and getting further and further away from just translating the file.
Exactly. And the ATLS study didn't just observe this anecdotally. They quantified it using highly specific temporal metrics. They utilized maximum mean discrepancy, MMD, and the global alignment kernel, or GAK.
Okay, wait. Let's pause on those terms. Maximum mean discrepancy and global alignment kernel. If I'm guessing based on the word temporal, are these metrics measuring time or the path the AI takes, rather than just the final answer?
Your intuition is spot on. Traditional accuracy metrics in AI are like checking the final answer on a student's math test. Did you get the translation right or wrong?
Right.
But MMD and GAK evaluate the trajectory that AI took to arrive at that answer. They are designed to detect structural and temporal inconsistencies.
So how wandering the path was.
Exactly. If you give an autonomous agent the exact same piece of COBOL twice, MMD and GAK measure how wildly different its internal thought processes were each time. In fully agentic systems, the drift was astronomical.
The AI would take vastly different, unpredictable paths every single time you ran the same prompt, which is terrifying for an enterprise. You do not want your core banking ledger translation to rely on a system that wakes up and decides to take a completely different, hallucinated scenic route to the answer today than it did yesterday.
Absolutely not.
So the alternative is the deterministic solution, which honestly, when I first read about it, sounded totally counterintuitive. We spend billions developing smart AI, and the solution is to hard-code its boundaries and treat it like a dumb machine.
If we look at the broader architectural reality, it actually makes perfect sense. Large language models are brilliant at semantic translation. They excel at understanding the meaning and intent of code.
Right.
But they are objectively terrible at project management and workflow routing. A deterministic pipeline acknowledges this limitation. It tells the AI, you do not get to choose what you do next. You will parse this specific file. You will output this exact JSON format. You will stop and wait for human validation. And under no circumstances will you loop more than 3 times.
You're putting heavy guardrails on the genius. You're separating the intelligence from the management. And the financial impact of those guardrails, according to the research, is staggering.
Oh, it really is. The ATLAS evaluation revealed that restricting the AI deterministically reduces token consumption by a massive factor of 3.5.
Wait, you are cutting the computational costs by more than 2/3 just by telling the AI to stop thinking so much.
Exactly. And we have to view this through the lens of token economics. The theoretical research cited in the sources actually views LLM tokens as production factors in a neoclassical economy.
Okay, so
Think of a token not just as a piece of data, but as raw material like steel or lumber in a factory. Every time the AI drifts into a reasoning loop, it is consuming raw materials. It is running up the enterprise bill.
the meter is running every time it hallucinates.
Exactly. There is a specific framework discussed in the papers called agent slimming. It dynamically prunes token consumption and enforces strict cost-aware boundaries on the AI's context window.
And how much did that save?
By implementing this, researchers saved up to 78.9% in sheer inference costs.
That's massive.
And then there is Evoma's evolutionary generation of multi-agent systems. This architecture treats the entire modernization pipeline as a rigid configuration problem.
So no freedom at all.
0. By forcing the AI into a strict, unyielding planner-evaluator-updater sequence, Evomas achieved a 98% execution reliability rate. It practically eliminated those unpredictable runtime exceptions because the AI physically lacked the agency to wander off the path.
So you lock the AI down to save millions of dollars in enterprise inference costs and guarantee reliability. That makes total sense.
Yeah.
But it brings me to a huge logistical hurdle. If the pipeline is rigidly controlled and we are dealing with a bank that has 10 million lines of heavily intertwined legacy code, how does the AI actually do the work without choking?
Right, the scale issue.
Yeah, I mean, even with guardrails, if you feed an LLM 10 million lines of code, its context window is going to explode.
That brings us to the absolute necessity of the division of labor. Modernizing legacy code is not a one-to-one linguistic translation. It is fundamentally a behavioral preservation problem.
I want to push back on that for a second, or at least play devil's advocate, because I think a lot of people might wonder this.
Sure.
Why can't we just treat this like Google Translate for code? LLMs translate English to French beautifully right out of the box. Why can't we just give a model a massive chunk of COBOL, prompt it with translate to Python, and hit enter? What is actually mechanically preventing us from doing that?
Attempting a direct linguistic translation triggers what the literature identifies as catastrophic context collapse. Let's look at your Google Translate analogy. French and English are both spoken languages designed for human-to-human communication.
Okay.
COBOL and Python are instruction sets designed for entirely different physical machines operating under entirely different architectural paradigms.
Right. COBOL is procedural, top-down instruction, and Python is usually object-oriented or functional.
Precisely. If you attempt a one-to-one translation, you lose the implicit business rules. You lose the edge case handling mechanisms that were designed for 1970s hardware. You lose the cross-module constraints.
It's just a totally different way of thinking.
Yes, a lot of COBOL relies on go-to statements jumping wildly across the code base. If you just translate that line by line, you don't modernize the system. You just create Python spaghetti code that is just as unmaintainable as the original COBOL.
You haven't modernized the house, you just painted over the termite damage.
Exactly.
To counteract this, the industry relies on architectures like the Agent Modernized framework. And this is where the research gets fascinating. This framework deliberately breaks the modernization pipeline into 4 distinct AI personas.
It's a very clever division.
It's like assembling a virtual engineering team where nobody's allowed to talk out of turn. Let's walk through these 4 personas. The first one is the legacy analyzer agent.
So the legacy analyzer agent is unique because it never writes a single line of modern code.
It just reads.
Its exclusive job is deep structural forensics. It ingests the raw legacy artifacts and maps out the structural skeleton. It looks for perform and call hierarchies.
To clarify for the listener, perform and call in COBOL are basically how the program executes subroutines or jumps to different sections of the code, right?
Yes. The analyzer maps all of those jumps. It maps the file I/O operations, the external database dependencies, and its ultimate output is something called a business rule inventory, or BRI.
What's in the BRI?
It isolates the conditional logic and the validation rules, and it encodes all of that into a massive, highly structured JSON document.
So it's the detective. It walks into the digital ruins, maps out what every room was supposed to do, and writes a sterile report.
Right.
Then that JSON report goes to the second persona, the specification generator agent.
This is the crucial abstraction layer. The specification generator takes that JSON report from the analyzer and physically separates the business logic from the raw COBOL syntax.
It pulls them apart.
It builds an intermediate representation. It essentially says, I do not care how COBOL executed this mathematically on a mainframe. The core conceptual goal of this block of text is to calculate compound interest based on these 3 variables and ensure the result is positive.
It's conceptually bridging the gap. It strips away the 1970s baggage and just leaves the pure business intent.
Yes.
And that leads to the third persona, the modernization transformer agent. This is the one that finally writes the Python.
But the architecture implements a brilliant constraint here. The transformer agent is completely blind to the original COBOL text.
Wait, it never even sees it.
It is never allowed to see it. It only consumes the abstract specifications output by the generator. Because it is totally isolated from the legacy syntax, it cannot mimic the procedural spaghetti code.
Oh, wow. That is so smart.
It is forced to generate target code strictly based on the abstract logic, ensuring the new code aligns perfectly with modern cloud-native standards, like utilizing fast API endpoints or setting up event-driven microservices.
You hide the bad habits of the old code from the writer of the new code. You just hand them the pure intentions.
Precisely.
And then the fourth and final persona is the equivalence validator agent.
The critic. It takes the newly generated Python, references back to the original specifications, and rigorously tests it. If the Python fails to meet the specification, the validator routes it back to the transformer for iterative correction.
But wait, mechanically, how do they pass all this information around without breaking the system? You mentioned that the business rule inventory is a massive JSON document. The sources mention these architecture diagrams frequently hitting 22,000 tokens.
They do get that large.
Doesn't passing a 22,000 token file back and forth instantly blow out the context window of these models?
State management at this scale is a massive orchestration challenge. The frameworks solve this using directed graph execution engines, specifically tools like LangGraph.
Okay, I want to visualize LangGraph. Instead of a CEO handing over a 500-page report, is it more like a massive library system? The AI doesn't carry all the books in its arms at once. It just holds a handful of index cards that point to the specific paragraphs it needs at that exact millisecond.
That is a highly accurate mechanical metaphor. LangGraph maintains a localized shared state object. The main routing agent isn't forced to read the entire 22,000 token JSON file on every pass.
Because that would be incredibly expensive.
It would exhaust its memory and drive inference costs through the roof. Instead, it delegates. It passes a pointer to a specialized subagent whose only job is to extract, distill, and summarize the critical vectors relevant to the current task and pass back a small localized summary.
So it only gets what it needs.
It manages the epistemic trust scope. meaning the AI only knows what it absolutely needs to know to take the next step without hitting the token context limit.
Okay, so the key to this entire multi-agent system, the thing that prevents the Google Translate disaster we talked about, is that middle step, the abstraction layer.
Yeah.
What exactly is the specification generator making? You said it builds an intermediate representation, but what does that actually look like on a screen?
This brings us to the core of the Agent Modernized framework, and mathematically it is incredibly elegant. The output is called a behavioral specification graph, or BSG.
Behavioral specification graph. The sources get pretty heavy into the math here, throwing around tuples and algebraic notation.
They do because the math is the only way to guarantee fidelity. The BSG is what forces all that convoluted, implicit legacy logic to become explicit, structured, and inspectable by a human engineer.
Okay.
Structurally, it is a directed acyclic graph represented by a specific tuple, VEE, pre-post in V.
Okay, I have my metaphorical notebook out. Let's break down that tuple. VE pre-coast in V. I'm going to guess V and E stand for vertices and edges, like a literal geometry graph.
Exactly. V is the set of operation nodes, or vertices. Think of these as discrete, isolated business operations. For example, a single node might be calculate interest compound or validate account status.
Got it. The actions, the points on the map. And E, the edges, are the lines connecting them.
The edges define the strict control flow and temporal dependencies between those operations. It dictates the sequence.
Like an order of operations.
Right. The edge dictates that you cannot execute the calculate interest node until you have successfully passed through the validate account status node.
Makes total sense. The arrows connecting the actions. Then we have pre and post. I assume those are preconditions and postconditions?
They are the environmental guardrails. Pre maps the required preconditions that must be satisfied before a node can safely execute.
Like checking the balance first.
Exactly. If an account balance is negative, the precondition to apply a standard interest rate might fail, triggering a different node. Post establishes the mathematically expected output states after successful execution.
And finally, INV, which stands for invariant. This feels like the most intense one.
It is arguably the most critical component for enterprise systems. INVM denotes the rigid invariance that must hold true throughout the entire operation, regardless of what path the code takes. These are non-negotiable systemic rules.
Like what? What's an invariant in bank?
Cryptographic validation limits are one. But the most common is the absolute rule of double entry accounting. The debits must always universally equal the credits.
Oh.
The total balance of the system cannot change during a transfer. If money leaves one account, it must appear in another. The BSG mathematically encodes that invariance so the AI cannot accidentally generate Python that destroys money.
And does it work? When they actually point this multi-agent framework at old mainframe code, does the AI successfully extract all these rules into the BSG?
The empirical evaluation from the 2026 literature is stunning. The BSG architecture successfully captured 91.2% of gold standard business rules from highly complex legacy environments.
Over 90%. That is incredible for code that has no documentation.
It confirms something vital for the industry. The primary bottleneck in legacy modernization isn't actually extracting the logic from COBOL. The AI is remarkably good at reading it.
The reading isn't the problem.
Right. The hardest part is the subsequent generative synthesis of the modern Python. But because the BSG formalizes the logic into this structured mathematical graph, it creates a traceable audit trail.
Which is absolutely massive. A bank or a government agency can't just deploy AI-generated code and tell a regulator, well, the black box said it works, so trust us.
They would be shut down instantly.
Exactly. Global finance regulators, the defense industry, healthcare compliance officers, they demand an inspectable artifact. If an auditor comes knocking, you don't show them the LLM prompt, you hand them the BSG.
It provides the required transparency. But we have to remember, a COBOL program isn't an isolated island. It doesn't exist in a vacuum. A mainframe application is an intricate, highly coupled ecosystem.
Right. Earlier you mentioned JCL and CICS. A single transaction doesn't just hit one file. The blast radius is huge.
The blast radius is the entire enterprise. A single business process like processing a mortgage payment might span dozens of distinct COBOL programs, rely on hundreds of external data copybooks, and trigger thousands of systemic interdependencies.
It's a web.
Yes. Bash jobs orchestrated by JCL are reading massive datasets written by CICS transactions, which are simultaneously calling IMS databases backed by DB2 tables.
It's an entire city of infrastructure, not just a single building.
Yeah.
So how does the semantic mapping handle the city? It can't just translate one birding into Python and ignore the roads connecting it.
The agents build structural mappings for the entire topography. And when they generate the target Python code, they remap those legacy ecosystem functions to modern cloud equivalents.
So they replace the roads, too.
Exactly. So a legacy JCL entry point, which, again, used to run a massive overnight batch job on magnetic tape on the mainframe, is modernized into an AWS step function or an Amazon event bridge trigger.
Oh, wow. So they are mapping 1970s hardware-level orchestration directly to 2026 cloud-native serverless orchestration.
Yes. CICS transaction boundaries, which handle real-time user inputs, are refactored into Python-based REST APIs deployed on AWS Lambda or EKS containers.
That's a huge leap.
And those old DB2 database calls, the AI automatically remaps them to utilize modern object relational mapping libraries like School Alchemy, querying against managed PostgreSQL backends in the cloud.
Here's where it gets really interesting, though. Mapping the architecture to the cloud is one thing. That's just changing the plumbing. But mapping the way the 1970s hardware actually stored memory.
Oh, this is the hardest part.
The sources point out that this is the most treacherous, mine-filled part of the entire translation, the CoMP3 data challenge.
The CoMP3 data format. This is the exact point where single-prompt, naive LLM approaches go to die.
Okay, I was trying to come up with an analogy for this based on what I read. Trying to translate COBOL memory structures to Python is like trying to translate the mechanics of a 19th century mechanical pocket watch into a digital smartwatch app.
I like that.
In the physical pocket watch, every single brass gear, every microscopic spring, has a strict physical mathematical weight and position. It was designed perfectly for the constraints of physics.
Right.
And a generic AI comes along, looks at it, and just tries to write an app that says, show the time, completely ignoring the physical gears.
Yeah.
But in financial code, you need the gears to match exactly where the math breaks.
That is an excellent mechanical analogy. COBOL was explicitly designed to interact with mid-century mainframe hardware to process financial mathematics with exact, unyielding precision.
It's not flexible.
Not at all. It doesn't use the standard 16-bit or 32-bit floating point variables we use today in Python or C++. It uses PIC picture clauses and OMP3, which stands for packed decimal.
Packed binary coded decimal, or BCD. Let's really get into the weeds here. How does that actually work at the hardware level?
It is deeply optimized to save space on magnetic disks. In standard modern computing, an entire byte 8 bits might be used to store a single digit, like the number 4. But in CMP3, numerical data is tightly packed.
Oh, tight.
Yeah.
Very. A PIC 94 representation maps each individual digit to exactly 4 bits. So the number 4 is literally stored in binary as 0102. The number 5 is 0101.
Wait, 4 bits per digit? That's half a byte.
Yes. And here is the mind-bending part that derails modern AI. To save memory, COBOL appends a nibble, which is the actual technical term for half a byte to the absolute end of the byte sequence solely to denote the mathematical sign of the entire number.
A nibble.
A nibble. Specifically, a hexadecimal value of 0xc at the end of the sequence denotes a positive integer, 0xd denotes a negative integer, and 0xf implies an unsigned value.
That is incredibly specific hardware-level optimization. They were fighting for every single byte of storage back then.
They had to. And it gets worse for the AI trying to translate it. Decimal placements in COBOL memory are often entirely virtual.
Virtual decimals.
They are dictated by a V notation in the source code.
Yeah.
So if you see PIC92V92, that implies a 2-digit integer followed by 2 decimal places, like $15.50.
But that decimal point doesn't physically exist in the hardware memory on the disk. The software just knows where it should be based on the length of the string.
So going back to my pocket watch analogy, what happens if the generic AI ignores the gears and just maps this CoMP3 data to a standard Python float or integer type?
It results in a catastrophic floating point rounding error. If you map a fixed point financial currency value from a mainframe to a Python float, the inherent imprecision of binary floating point arithmetic will slightly alter the pennies over millions of transactions.
Oh, no.
Yes. 0.1 plus 0.2 in floating point math often equals 0.30000000004. You will silently corrupt millions of financial records during a migration. Money literally vanishes or appears out of nowhere in the ledger.
The danger of the float.
Yeah.
You can never, ever map currency to float. So what is the solution? How does the multi-agent system fix this memory problem?
The AI must be explicitly prompted and constrained to map these specific PIC and COMP3 signatures to Python's decimal module, or use highly specialized custom parsing libraries.
It has to perfectly emulate the old math.
Furthermore, you cannot use standard ASCII decoding when moving the data. If you convert the mainframe's native EBCDIC encoding to ASCII using standard text tools, the translation will literally corrupt the binary payload of those packed sign nibbles.
It ruins the data in transit.
The AI has to ensure exact byte-for-byte binary fidelity during the transfer.
Okay, so let's say the AI miraculously navigates this minefield. It builds the BSG, it maps the JCL batch jobs to the cloud, it avoids the flow trap, and perfectly maps the COMP3 memory to decimal.
That's a lot of ifs, but okay.
Right. How do we prove it? How do we prove to the board of a massive bank that the new code actually works before they flip the switch and route trillions of dollars through it?
You're touching on a massive vulnerability in the whole process, and it brings us to what the researchers call the testing paradox.
The testing paradox.
The paradox is this. Companies that already possess comprehensive, high-coverage automated test suites don't strictly need AI to modernize.
Because they can just test their way through manual rewrites.
Exactly. They can refactor their code using standard deterministic tools because they have a massive safety net to catch any errors. But the companies that are most desperate to use AI for modernization almost never have existing tests for their mainframes.
Because the code was written 40 years ago, long before test-driven development was a standard practice. The original authors just wrote the code, saw that it worked, and moved on.
So if you have no existing tests, utilizing an LLM to rewrite your core logic introduces massive, unquantifiable risk. Think about the math here. A 1% hallucination rate from an LLM across a 1 million-line enterprise repository yields 10,000 silent defects.
10,000 bugs injected straight into the core banking system. That is an unacceptable risk profile.
Completely unacceptable.
So without historical tests, how do they create an empirical ground truth to measure against?
Through automated differential testing. Since there are no human-written tests, the equivalence validator agent uses the mathematical constraints of the BSG. We discuss the preconditions, postconditions, and invariants to autonomously generate hundreds of synthetic inputs.
It makes up its own test data.
Right. It looks at the mathematical boundaries and tests the extreme edge cases.
And then it runs a race between the old and the new.
Precisely. It feeds those synthetic inputs through the original COBOL implementation, often using a mainframe emulator or a localized new COBOL runtime, and simultaneously feeds them through the newly generated Python environment.
And it strictly compares the outputs.
It forces a paradigm shift in how we view code quality. We stop caring about structural similarity. We don't care if the Python looks like the COBOL or follows the same procedural steps.
Right. The internal logic doesn't matter as long as the answer is the same.
We focus purely on strict behavioral fidelity. Does the Python output the exact same byte string as the COBOL when given the exact same input?
But what happens when they don't match? Because with AI, especially with the complexity of COMP3 we just talked about, they are definitely going to fail sometimes.
They fail a lot. This is where environment-in-the-loop validation becomes the cornerstone of the architecture. If a differential test fails, say there's a COMP3 mismatch, or an indexing error in Python that mimics a null pointer exception, the system doesn't just crash and report a failure to a human.
What does it do?
The error logs, the execution trace artifacts, and the test results are captured within a secure, isolated CICD Docker container. And all of that failure data is piped straight back into the prompt context of the LLM validator agent.
It's an automatic closed feedback loop. The AI writes the code, the Docker environment tests it, fails it, hands the AI the error log, and essentially says, you broke the gear. Here's exactly how it broke. Fix it.
Exactly. The model diagnoses its own runtime failure, refactors the Python code, and iteratively pushes it back into the container until the differential test passes.
Oh.
And the empirical reality check on this from the 2026 data is brutal, but incredibly illuminating.
I have the benchmark stats right here, and these numbers blew my mind. The researchers ran tests without this feedback loop first. They just asked the models to translate zero-shot, meaning one prompt, one answer.
Right, no retries.
And the models achieved a 0.0% behavioral equivalence rate. 0. Every single frontier model completely failed to produce functionally equivalent code across the board on the first try.
It's too complex for zero-shot.
Yeah. And with the environment in the loop feedback mechanism active.
With the loop, Codex hit 19.4%, GPT-4o hit 8.1%, and GPT-4 Mini hit 9.4%.
Now, to a layperson, an 8% or 19% success rate sounds abysmal.
It does.
It sounds like an F-. It sounds like the technology doesn't work.
It does sound that way. But in the context of enterprise legacy modernization, what these numbers actually prove is that dynamic runtime error catching is functionally mandatory.
You literally can't do it without the loop.
Exactly. Without the feedback loop, LLMs are fundamentally incapable of executing zero-shot legacy translation. The relative delta between 0% and 19% is the difference between impossible and possible with iteration.
It proves the framework has legs.
It proves the architecture works, even if the underlying foundational models still struggle with the sheer density of the complexity.
That is a fascinating way to look at it.
Mm-hmm.
The architecture is sound, but the brain inside the architecture isn't quite there yet.
Right.
The low success rates of frontier models like GPT-4o reveal a major problem. They are generalists. GPT-4o can write a sonnet in the style of Shakespeare, it can code a website in JavaScript, it can summarize a recipe.
But it's not a mainframe engineer.
Exactly. It just doesn't know enough about the deep, dark corners of 1970s mainframe memory allocation.
Yeah.
So what is the industry building right now to fix the brain?
They are abandoning general models for this specific task and moving aggressively to domain-adapted specialized AI.
So training them just on COBOL.
Right. Standard evaluation datasets like the NIST COBOL 85 suite that a lot of models train on are just too simple. They consist of isolated 1,200-line programs. They don't reflect the systemic complexity of a real telecom or financial repository, which have millions of interdependent lines.
It's not a realistic test.
General LMs fail in those real-world environments. So researchers built models like COBOL Coder.
COBOL Coder, released in April 2026.
It is a deeply specialized, domain-adapted model, fine-tuned entirely on curated enterprise data. And the training methodology is the key differentiator here.
How did they train it?
They used a multi-stage, compiler-guided validation pipeline during training. That means they only fed the model structurally sound, semantically rich, and syntactically flawless COBOL programs that successfully compiled.
So no garbage data.
Exactly. They didn't just scrape GitHub for random broken COBOL snippets. They ensured pristine data quality to drastically reduce hallucination drift.
And the benchmark domination is crystal clear. When you look at the COBOL level task, COBOL Coder achieved a 73.95% compilation success rate, almost 74%.
Compared to GPT-4o.
Yeah, GPT-4 was only 41.8%. And for functional correctness, the pass at 1 accuracy, COBOL Coder hit 49.33, while GPT-4 was stranded at 16.4.
And how did the open source general models like CodeLlama and StarCoder 2 perform on those benchmarks?
Near zero. They basically failed to even produce code that a compiler would accept.
The data supports the conclusion entirely. These metrics definitively prove that relying on general-purpose models for enterprise legacy modernization is a highly flawed strategy.
You need a specialist.
You need a model that implicitly understands the exact memory mapping of a PIC9 clause without having to be prompted.
And this isn't just happening in academic research papers. The sources show real-world enterprise vendors backing this exact specialized approach right now. We have AWS Transform for Mainframe.
Yeah, AWS recognized the severe risks of raw, unguided transpilation early on. AWS Transform uses human-in-the-loop workflows alongside automated decomposition.
How does their specific system work?
It leverages Agentic AI to reverse engineer technical documentation and map out those massive JCL dependencies we talked about. It extracts the business logic into microservice specifications via their proprietary Kiro system, and it maps natively to the AWS cloud ecosystem.
How does that actually speed things up, though?
By automating the dependency mapping, the Kiro system eliminates the months of human labor usually required just to figure out what the code base does.
Oh, because humans aren't spending weeks just reading old files.
Right. AWS is claiming reductions in migration timelines from multiple years down to several months.
Years down to months. That is a massive paradigm shift for a bank facing a demographic cliff. And IBM isn't sitting out either. They launched Project Bob, which became generally available as IBM Bob in early 2026.
IBM Bob is fascinating because of how it is deployed operationally. It doesn't act as a detached transpilation engine running batch jobs in the background. It integrates directly into the developer's integrated development environment, or IDE.
Like VS Code?
Yes, it functions as an AI-first coding partner sitting right next to the developer. It orchestrates workflows across COBOL, PLI, RPG, and JCL.
So it's right there while you're working.
It automatically modernizes frameworks and writes compliance-ready code for highly regulated environments like HIPAA in healthcare or FedRAMP in government, while doing inline security scans with tools like SemGrep.
And again, how does it actually achieve the productivity gains? The adoption metrics are wild. 80,000 initial users, and they reported a 45% productivity gain during multi-step modernization workflows.
It achieves that 45% gain by drastically reducing context switching. The developer doesn't have to leave their IDE to look up how a specific PLI routine handles memory.
The AI just does it.
IBM Bob generates the compliant Python inline, runs the SemGrup security scan instantly, and surfaces any vulnerabilities before the code is even committed. It treats legacy environments as first-class citizens in modern CI/CD pipelines.
So what does this all mean? If you are a CTO listening to this right now, and your senior COBOL architect is retiring in 6 months, taking 40 years of institutional knowledge with them, what is the playbook? Based on all this 2024 to 2026 research, what is the concrete enterprise roadmap?
The consensus across all the empirical data points to a hybrid orchestration model. It's a rigorous 4-step synthesis. Step 1, map the ecosystem.
Okay, map it out.
You must use a deterministic pipeline to map the blast radius. You crawl the JCL, the DB2 schemas, the CICS entry points, and you build a comprehensive knowledge graph. And the cardinal rule of step 1 is never, under any circumstances, start by prompting an LLM to generate code.
Right. Don't let the AI start building a new house until you know exactly where every single pipe and wire in the old building goes.
Exactly. Step 2, semantic abstraction. This is where you bring in the math.
The BSGs.
Yes. You generate the behavioral specification graphs, the BSGs. You turn the code into a mathematical tuple. You capture the preconditions and invariants. And this creates the verifiable trust boundary for your human architects to verify the logic.
Step 3, domain-adapted transpilation.
Right. You take that BSG and you feed it into a specialized domain-adapted model, like COBOL coder, not a general frontier model.
Because general models fail.
And you enforce strict constraints, like the decimal mappings to guarantee hardware memory fidelity. You bypass the original COBOL text entirely to prevent context contamination and spaghetti code replication.
And the final step, step 4, deterministic validation.
You execute automated differential testing. You run the synthetic inputs through the old mainframe emulator and the new Python environment. You use environment-in-the-loop feedback with hard-coded retry limits to prevent token bankruptcy.
Until it's perfect.
And you do not merge to production until you hit a 100% behavioral equivalence rate.
Wow.
Implementing this roadmap is no longer an innovative luxury for forward-thinking tech companies. With the demographic collapse of the silver tsunami, executing this 4-step pipeline is an absolute operational necessity to survive the next decade.
Well, I want to thank you for guiding us through this. This is dense, uncompromising stuff, mathematical graphs, hardware memory architectures, hexadecimal nibbles. But you really illuminated the mechanical reality of what it takes to modernize the systems that keep society running.
It's a critical challenge, and it's essential that we understand the deep mechanics behind the solution rather than just relying on the surface-level hype of AI translation.
And that brings us back to where we started, that invisible crumbling bridge. We are sending highly constrained, deterministic AI teams into the digital ruins of the 1970s to build us a brand new infrastructure.
Yes, we are.
But I want to leave you, the listener, with a final thought to mull over. If we are using highly complex multi-agent LLMs to translate monolithic undocumented COBOL into millions of lines of highly abstracted AI-generated Python, are we actually solving the silver tsunami?
That's the real question.
Or are we simply creating a brand new generation of hyper-complex cloud-native legacy code that, 50 years from now, only another AI will be able to understand and maintain? Something to think about next time you swipe your credit card. Thank you for joining us on this deep dive, and keep exploring the hidden systems running our world.